This video is on the practice problem we did in class from the PowerPoint for 2.1.6, calculating truss forces. So I'm just going to redo the whole thing. Even though we did it in class, I thought I'd do it in the video form so that as people go through the practice problems or review for tests later this year, you can refer to this video to refresh your memory on how to go about solving a truss, a simple truss. So for starters, you want to make sure you have the problem fully defined. So you need your distances of each of the members, the angles. The first thing I would always do is find your angles of each of your members. And from there, the first real step is going to be drawing your free body diagram. Okay, that's always step one. So we can go ahead and draw out our free body diagram for this truss. It'll look something like this. And I may as well label them right now. A, B, C, and D, just like they are above. I'm going to go to the find point. And what we find is, in terms of our forces, we have one load of 500 pounds coming straight down from point D. And then we have to come back up here and look at our supports. We have a pin support on the left, and a pin support, as we all know, gives a reaction force at A in both the Y direction and the X direction. So we go ahead and label those. At C, there is no horizontal reaction force because we're allowed to slide horizontally, but we still have a reaction force at C in the Y direction. So if you look, we have this external forces table of forces. What I'd recommend you do is take the table as such somewhere on your page. Put a little boxed in area and list out all the unknown values. You want to take the reaction forces and the given forces. So if you look up here, I have my reaction force at A, both in the X and Y direction, and the reaction force at C in the Y direction. And then the last thing I do is I put in my known 500 pounds. So I can fill these in as I go. The 500 was already given in the problem statement. And then we are ready to actually solve the external forces. So external forces are these reaction forces, the given 500 pounds. And in order to do that, what we do is we calculate our moment. We calculate the sum of our moments. So how are we going to know how to do the sum of the moments? In terms of where do we start? So we know that the sum of the moments have to equal 0. But you don't just say the sum of the moments, because the moment could be from anywhere. The moment could be from point A, or it could be the moments at B or D or C. It doesn't really matter. They can happen anywhere. And you can calculate them from anywhere. But we are going to choose point A as our reference point. And the reason being, as I said in class, if we choose A to be our our reference point, what happens is the moment of reaction force A in the X direction becomes 0. And the reaction force at A in the Y direction becomes 0 because your distance from the fulcrum or the pivot is 0. So in doing that, I'm going to label that as the moments about A, and they should sum to 0. So the two moments we have are 500 pounds. You know what? I'm going to actually change this to our find marker. That's 500 pounds at point D. So your force times your distance is given right here as 3 feet. And at some point here, we need to clarify that this moment is going to act in a clockwise direction, and because it's clockwise, that means that this moment is considered negative. So the moment at D plus the moment at C, because that's the other place we have a reaction, or a force in general, but in this case a reaction force. So we have an upward direction, so that's gonna give us that counterclockwise moment. So we know that that's a positive. So force R of C in the y direction times distance. Now your distance is not 7 feet. That's one of those places that a lot of people get tripped up on very easily. That distance from C has to go back to the reference point A, perpendicular. And in this case, that 7 plus 3 gives us 10 feet. So moment at D plus moment at C should equal 0. So I'm going to write that out, negative 1,500. And the units would be foot-pounds. Plus, I'm going to rearrange 10 times reaction C in the y direction equals 0. So 10 times reaction of C in the y equals, I'm just moving the 1,500 over, so reaction force at C in the y direction equals 150 pounds. This is foot pounds, and this is just feet. So when you divide both sides by 10, feet divided by feet gives you just units of pounds. So we have reaction force of C in the y direction. So I'm going to go right away. I'm going to fill in my table. RCY is 150 pounds. I'll actually make that a little bit smaller. Let's see. Next, we can look at, well, we have both of our reaction forces at A, X and Y. How are we going to go about solving those? Well, we can look at the sum of the forces. Let me make this bold. In the y direction. So the sum of all forces in the y direction must be 0. Now, had we done this first, we'd be in trouble because we had the reaction force of C in the y direction, 500 pounds, and the reaction force at A in the y direction. That's two unknowns with one equation. We would have been in trouble. We would not have been able to solve because we'd have too many unknowns. But because we took our moment and summed our moments to 0 first, we found reaction force C in the y direction. So we can write that as 0 is equal to reaction force A in the y direction. I'm just going from left to right. Minus 500 pounds. Keep in mind, minus because that force in the in the y direction is down, so that's negative. And the reaction of C in the y direction is positive, it's up, and that was 150 pounds. So in order to get that reaction force of A in the y direction, we simplify, and we get that the reaction force at A in the y direction is a positive, sorry, that should be a minus here, positive 350 pounds. There we go, we have another one down. So reaction force of A in the y direction, we fill that in as 350 pounds. And last thing we have is the sum of the moments, not the moments, the sum of the forces in the x direction. They must equal 0. We want static equilibrium, so they must equal 0. The nice thing about this is 0 is equal to, well, what forces do we have in the x direction? Well, we have reaction force of A in the x direction plus, well, look at here. Let's see, we have one reaction force in the x direction. This is pure vertical. This is a pure vertical. So we have nothing left to sum up. So I'm going to remove my plus sign and just say that the reaction force of A in the x direction is 0. The force, 500 pounds, has no x component whatsoever. So our reaction force is, is going to also be 0. So reaction force A of x direction is 0 pounds. We've solved all external forces. We are ready to move on and calculate our internal forces. We'll do that on the next video. So again, do your free body diagram first. Once you've identified all the reaction forces, you calculate the external forces and put them all into a nice neat table somewhere off to the side of the problem. And you're ready to move on.